The leaf trembles before the body does. A slight shift in air pressure, a shadow crossing from above, the soft percussion of approaching legs along the stem, and in an instant, the bright dome of the ladybug releases its grip. It drops without resistance, tumbling through the green architecture of the plant, striking a lower leaf and coming to rest as nothing more than a motionless speck. The transformation is immediate and absolute. Where there was a deliberate forager moving with measured precision among aphid colonies, there is now an inert bead of red against the foliage, legs folded tightly beneath the hardened shell, antennae drawn inward, all signs of animation erased. In ecosystems ruled by reaction time measured in fractions of a second, this collapse is not panic. It is strategy refined by millions of years of selection. Many predators in this layered canopy do not hunt by scent or by complex reasoning. They hunt by motion. Jumping spiders lock onto shifting outlines. Mantises calibrate distance through parallax as prey moves against the background. Even small birds, scanning from above, register flickers and tremors more readily than static shapes. Movement is the signal that separates food from leaf litter. When the ladybug releases its grip and enters tonic immobility, it interrupts that signal at the source. The neural circuits of its pursuer, primed to follow trajectory and velocity, lose their reference point. The tracking lock dissolves. What remains appears indistinguishable from debris. A seed, a blemish, a fragment of plant tissue. For predators optimized for pursuit, stillness can be invisibility. The physiology behind this sudden freeze is as precise as any mechanical system. Flexor muscles contract to draw the limbs inward, minimizing protrusions that might betray life. The exoskeleton, already convex and polished, reflects ambient light in a way that reduces shadow depth, flattening the insect's profile against the leaf. Even respiration becomes subtle, abdominal movements reduced to near imperceptibility. This is not a feint or a loss of control. It is a reversible neurological state triggered by tactile or vibrational cues, a rapid recalibration from active foraging to defensive suspension. Yet stillness alone is not always enough. Some predators investigate further, nudging the inert body with probing mouthparts or grasping it outright. If seized, the ladybug deploys a second, more visceral defense. From the joints of its legs, droplets of yellowish fluid begin to well and bead. This is reflex bleeding, a controlled exudation of hemolymph infused with alkaloid compounds that taste intensely bitter and can be mildly toxic to small vertebrates and arthropods alike. The chemistry is not accidental. These compounds are synthesized and stored specifically for moments like this, transforming the insect's own circulatory fluid into a deterrent. The effect is often immediate. A bird that expected a soft, neutral meal instead encounters a burst of acrid flavor. A spider senses chemical cues that signal unprofitability. The predator recoils, mandibles parting, beak opening to expel the offending taste. In that brief window of disgust, the ladybug does not spring to life. It remains limp, legs curled, body slack, extending the illusion of death. This continuation is critical. Sudden revival could reignite pursuit, but sustained stillness reinforces the narrative of inedibility and decay. To the predator, the experience resolves as a mistake rather than an interrupted hunt. Around this small drama, the aphid colony continues its quiet extraction of plant sap, and the broader web of interactions persists. The ladybug is both hunter and hunted, regulating herbivore populations while navigating its own vulnerability. Its vivid coloration, often interpreted as warning, works in concert with these behaviors, advertising the very chemical defense now tasted. But color alone does not guarantee recognition, especially to inexperienced predators. The collapse, the freeze, and the reflex bleeding form a layered system. Behavioral misdirection paired with chemical reinforcement. In this compact body, evolution has braided neurology, biomechanics, and biochemistry into a seamless sequence. A fall that looks like failure is, in fact, a calculated interruption of another creature's perception. A droplet of blood becomes a message written in bitterness. And survival hinges not on strength or speed, but on the precise manipulation of expectation within a world where attention is lethal. The branch appears unremarkable at first glance, one among hundreds weaving a lattice through the understory. Sunlight filters in fractured bands, illuminating bark textured with lichen and shadow. Along its length, a narrow extension juts outward at an irregular angle, segmented and matte, colored in the muted greens and browns of living wood. Only when the wind passes does the extension reveal itself as something more than timber. It sways, not independently, but in precise synchrony with the surrounding foliage, matching amplitude and rhythm as though tethered to the same invisible metronome. This is not coincidence. It is calibration. The stick insect has not merely chosen to resemble a branch, it has chosen to behave like one. Camouflage here is not a static condition, but an active performance shaped by sensory feedback. The insect's elongated body, reinforced by a rigid exoskeleton and articulated joints, provides the structural foundation for resemblance. Pigments diffuse across its cuticle in irregular bands that mimic the tonal interruptions of bark. Some species even bear small protrusions that resemble leaf scars or buds, imperfections that complete the illusion. Yet morphology alone cannot withstand scrutiny in a forest dense with predators whose vision is tuned to detect anomalies. Many birds and reptiles rely on edge detection and motion contrast, scanning for outlines that break the continuity of vegetation. A perfectly shaped body that moves at the wrong time is still a target. So the stick insect does not flee at the first disturbance. Flight would create a trajectory, and trajectories are invitations. Instead, it calculates. Mechanoreceptors along its legs register vibrations traveling through the branch, distinguishing the chaotic oscillations of wind from the deliberate pulses of approaching footsteps. Compound eyes, though less acute than those of predatory insects, detect shifts in light and looming shadows. When the environment moves in the diffuse, multi-directional pattern of breeze, the insect joins it, swaying gently to dissolve its outline within the collective motion of leaves and stems. This synchronized rocking reduces relative motion, a concept as critical in predator evasion as it is in aerodynamics. To the observer scanning for independent movement, nothing stands apart. The transformation becomes more striking when danger draws close. As a bird lands nearby, or a lizard advances along the branch, the insect's behavior shifts from fluid mimicry to absolute stillness. Muscles contract and lock, converting the flexible body into a rigid rod. Antennae align with the axis of the torso. Legs extend or clasp in positions that reinforce the illusion of woody growth. This sudden freeze is not hesitation, but erasure. By eliminating motion entirely, the insect withdraws from the sensory world of its predator. Many hunters rely on change detection. A stationary object that has already been categorized as background is often filtered out by the brain's own efficiency. The prey does not outrun the predator. It exits the predator's perception. There is an additional layer of deception embedded in timing. The stick insect often allows a predator to approach within unsettling proximity before committing to stillness. Early freezing might draw attention to the moment of change, but freezing precisely as the predator's focus shifts elsewhere allows the insect to vanish between glances. This calculated pause reflects an evolutionary negotiation between risk and invisibility. Too much movement, and it is seized. Too little responsiveness, and it may fail to match environmental cues. Survival depends on reading the forest's subtle signals with extraordinary precision. Even thermoregulation plays a quiet role in this performance. By aligning its body with the branch and minimizing exposed surface area, the insect reduces thermal contrast that might otherwise betray it to predators capable of detecting slight temperature differences. Its elongated form also facilitates convective cooling, allowing it to remain motionless in humid heat without overheating, a necessity when escape depends on endurance rather than speed. In this theater of leaves and light, fake death becomes something more nuanced than collapse. It is the disciplined choice to stop existing as a separate entity within the landscape. The stick insect does not simply imitate a branch. It becomes statistically indistinguishable from one, exploiting the perceptual shortcuts of its enemies. Predators eventually shift their gaze, attention sliding elsewhere in search of easier prey. The branch remains. The illusion holds. And in a forest where attention can be fatal, the most convincing act is not dramatic movement, but the deliberate disappearance of all motion at exactly the right moment. In the dim understory of a tropical forest, where light arrives filtered through layers of canopy and the air hangs heavy with moisture, a butterfly rests against the trunk of a tree. Its wings are folded vertically, exposing a surface patterned in muted browns and soft grays, textures that echo dead leaves and peeling bark. At rest, it is nearly indistinguishable from the debris scattered across the forest floor. This is the owl butterfly, a creature whose survival depends not on speed alone, but on the careful orchestration of perception. Here, deception unfolds not as disappearance, but as transformation. A lizard inches along the trunk, guided by acute motion detection and depth perception honed for close-range strikes. Its visual system is tuned to contrast and sudden shifts, to the subtle tremor that reveals living tissue among static forms. For several seconds, the butterfly remains inert, relying on camouflage that merges it with the vertical plane of the tree. Its wing coloration, shaped by evolutionary pressures from countless predatory encounters, absorbs the ambient light rather than reflecting it sharply, reducing visual edges that might draw attention. In this folded state, it resembles nothing worth pursuing. The moment the lizard lunges, the butterfly executes a rapid and forceful wing display. The closed wings snap open in a fraction of a second, exposing large circular eye spots on the dorsal surface. These markings, ringed with high contrast bands of black, yellow, and pale blue, create the sudden appearance of enormous staring eyes. The transformation is abrupt enough to interrupt the predator's neural processing. For an animal that relies on rapid threat assessment, the unexpected emergence of a face-like pattern can trigger hesitation. This response is not superstition or imagination. It is rooted in deeply conserved visual circuits that prioritize potential threats. Many vertebrates possess innate biases toward eye-like shapes, as eyes often signal the presence of a larger organism capable of retaliation. In that fraction of suspended decision-making, the butterfly has already altered the script of the encounter. The lizard, primed for a small and manageable insect, is confronted with a visual cue suggestive of something larger. The eye spots do not need to perfectly replicate a predator's face, they only need to generate uncertainty. Studies of avian and reptilian predators demonstrate that even brief hesitation can determine the outcome of an attack. A missed strike expends energy and risks injury. In ecosystems where caloric budgets are tightly balanced, uncertainty carries cost. Yet the display is only half the strategy. After the initial flash, the butterfly often drops or shifts position and becomes completely still, wings partially open or closed depending on context. The stillness is deliberate. Once the predator's attention has been disrupted, motion would re-establish it. By freezing in place, the butterfly allows the predator's perceptual system to recalibrate. Without continued movement to anchor focus, the brain's attention mechanisms drift, especially when competing stimuli in the forest demand processing. The predator's strike sequence, once initiated, dissolves into indecision. The ecological role of this butterfly extends beyond individual survival. As a consumer of fermenting fruit and plant sap, it participates in nutrient cycling within the forest floor community. Its larvae feed on specific host plants, linking canopy growth to understory dynamics. The eye spots themselves may also serve multiple functions, including deflecting strikes toward less vital wing margins. A predator that bites at the conspicuous marking may damage expendable tissue while sparing the body, allowing the butterfly to escape with torn but functional wings. Such trade-offs illustrate how natural selection balances risk, reproduction, and longevity. Thermoregulation plays a subtle part in this strategy as well. The large surface area of the wings allows rapid absorption of diffuse sunlight when needed, enabling short bursts of flight in the humid shade. But during a defensive display, the sudden exposure of dorsal patterns also alters how light reflects toward the predator, enhancing contrast precisely when it matters most. The butterfly manipulates both color and behavior to control interpretation. In this encounter, no chemical weapon is deployed, no physical armor relied upon. Instead, the butterfly intervenes in the predator's mind, rewriting the narrative of what stands before it. The attack is not defeated through force, but through interruption of certainty. A flash of false eyes arrests the strike, and disciplined stillness seals the illusion. Within the layered complexity of the forest, survival sometimes depends less on vanishing and more on convincing an enemy that it has misjudged reality itself. At the edge of a meadow where tall grasses dissolve into shrubs and wildflowers, a praying mantis clings to a vertical stem, its body aligned with botanical geometry so precisely that it appears grown rather than perched. The thorax extends like a living petiole, the abdomen tapering in soft green segments that mirror the veins of surrounding leaves. Its raptorial forelegs, folded in the familiar posture of ambush, are drawn close to the body, reducing silhouette. In this posture, the mantis is often imagined as a hunter suspended in expectation, a predator defined by the violence of its strike. Yet in a landscape threaded with birds, reptiles, and small mammals, the mantis is equally defined by restraint. The same patience that allows it to seize prey also allows it to survive as prey. A breeze passes through the meadow, bending stems in slow arcs. The mantis moves with it, not as an independent agent, but as a compliant extension of the plant. This coordinated sway is not passive. Sensory hairs along its legs and body detect air currents and substrate vibration, allowing it to match oscillations with subtle muscular adjustments. The insect's compound eyes, mounted on a flexible neck capable of remarkable rotation, track changes in the environment without requiring the body to shift. This separation of visual surveillance from gross movement is critical. Motion attracts attention, stillness deflects it. When a shadow sweeps overhead, cast by a foraging bird, the mantis transitions into a deeper state of immobility. Muscles lock along the thorax and abdomen, freezing the insect mid-sway. The triangular head tilts slightly downward, aligning its contours with the stem's axis. Unlike the dramatic startle displays some mantis species employ, with flared wings and eye-like markings, this is a different strategy entirely. It is a defensive shutdown, a calculated withdrawal from the perceptual field of the predator. Many avian hunters rely on detecting discontinuities in pattern and motion within complex vegetation. A mantis that remains absolutely still merges into the statistical background of vertical lines and green surfaces. To the scanning eye, it becomes noise rather than signal. This stillness is physiologically demanding. Unlike vertebrates that can rely on endothermic regulation to maintain muscle readiness, the mantis depends on ambient temperature to power its movements. In cooler conditions, prolonged immobility risks reduced responsiveness. Yet its exoskeleton and internal tracheal system allow oxygen to diffuse directly to tissues, even when external movement ceases. The insect can sustain this suspended state for extended periods, conserving energy while remaining prepared for sudden action. The neural circuits that govern its predatory strike remain primed, but inhibited, a balance between readiness and restraint. Predator avoidance in mantises reveals an evolutionary duality. Their forelegs, armed with spines designed to grip struggling prey, could offer some measure of defense, yet engaging a larger predator would be futile. Instead, the mantis leverages the same cognitive simplicity that defines many of its enemies. Birds and lizards must filter immense sensory input to function efficiently. Objects that do not move and do not break pattern are deprioritized. By refusing to animate itself, the mantis effectively edits itself out of the predator's immediate concern. Only after the bird has settled elsewhere, attention redirected toward more conspicuous insects, does the mantis resume its subtle swaying. Life re-enters the posture gradually, as if the plant itself has begun to breathe again. The transformation is understated, but profound. What moments earlier resembled lifeless debris regains agency and intent. Soon a grasshopper ventures too close, unaware that the rigid stem conceals a predator. The mantis's forelegs extend in a motion too fast for most prey to register, spines interlocking around the thorax of its victim. In this interplay of concealment and aggression, the mantis demonstrates that predation and evasion are not opposing skills, but reflections of the same principle: control over movement. To hunt successfully requires the discipline to remain unseen until the precise instant of attack. To avoid being hunted requires the same discipline extended further, suppressing action until danger passes entirely. Within the layered vegetation of the meadow, survival belongs not to the most active organism, but to the one that understands when to vanish into stillness and when to re-emerge with decisive force. Night settles heavily over the forest floor of Madagascar, where leaf litter forms a layered mosaic of decay and renewal. Beneath fallen branches and rotting logs, humidity lingers, stabilizing temperature and slowing desiccation in a habitat defined by moisture and shadow. Within this concealed architecture moves the Madagascar hissing cockroach, a broad armored insect whose presence is more often felt than seen. Its exoskeleton reflects faint glints of moonlight when exposed, but most of its life unfolds in crevices where wood meets soil. Here, survival is not built on speed across open ground, but on mastery of confined space. When disturbed, the cockroach does not sprint blindly. Its first response is directional and deliberate. Using sensitive antennae that sweep continuously through the air, it maps the immediate terrain, identifying narrow fissures in bark or the thin gaps between layered debris. The body, already dorsoventrally flattened compared to many other insects, lowers further as flexible membranes between abdominal segments compress. Legs splay outward to distribute force, claws gripping irregular surfaces as the insect presses itself into a crack barely wider than its own thickness. Once lodged, it becomes a biological wedge. This wedging behavior transforms the physics of predation. A bird's beak or a small mammal's snout relies on leverage to extract prey from hiding places. By expanding slightly within the crevice and bracing its spined legs against opposing surfaces, the cockroach increases friction dramatically. The predator encounters not a loose body to grasp, but an anchored structure resisting displacement. Even if partially exposed, the insect's exoskeleton provides a smooth, convex surface that reduces purchase for teeth or talons. In this posture, movement ceases almost entirely. The cockroach appears less like an animal and more like a dark knot in the wood. Stillness plays a critical role in this transformation. Many predators rely on tactile feedback to confirm that what they have encountered is alive. Subtle muscular contractions, attempts to escape, or shifting weight can trigger intensified effort. By entering a near motionless state once wedged, the cockroach reduces these cues. Its tracheal system continues to deliver oxygen directly to tissues without requiring visible respiratory motion. Neural activity persists, but outward signs diminish. The predator probing the crevice receives little reinforcement that further exertion will yield a reward. In the absence of confirming signals, attention drifts elsewhere. Yet the Madagascar cockroach adds another dimension to this defensive repertoire: sound. When grasped or cornered before reaching shelter, it can forcefully expel air through specialized spiracles along its abdomen, producing a sharp hissing noise. This sound is generated not by vocal cords, but by the rapid compression of internal air sacs, a rare capability among insects. In the quiet understory, the hiss is startlingly loud relative to the insect's size. For a predator accustomed to silent invertebrate prey, the sudden auditory burst can interrupt the attack sequence. The startle response is deeply embedded in vertebrate nervous systems. Unexpected stimuli demand reassessment. The hiss does not injure, nor does it last long. Its function is temporal. In the brief pause created by surprise, the cockroach pivots toward the nearest crevice and executes its flattening maneuver. The sound buys fractions of a second, but in ecological terms, fractions can determine survival. Once inside a crack and motionless, the insect abandons theatrics and returns to invisibility. Beyond these defensive behaviors, the cockroach plays a substantial ecological role as a decomposer, consuming decaying plant matter and contributing to nutrient cycling within the forest. Its robust physiology, including tolerance for variable humidity and a capacity to store energy efficiently, supports life in environments where conditions fluctuate between abundance and scarcity. The same durable exoskeleton that resists predatory grasp also protects against abrasion as it navigates coarse substrates. In this layered world of wood and shadow, survival depends on understanding structure as much as on sensing threat. The Madagascar hissing cockroach does not attempt to overpower its enemies. Instead, it manipulates space and perception, transforming its body into a locked component of the environment. A hiss fractures the predator's confidence, a flattened profile denies leverage, and disciplined stillness erases the final trace of prey. What remains is a silent, immovable presence within the crevice, indistinguishable from the forest itself until danger has passed. In the late summer meadow, where seed heads bow under their own ripeness and sunlight rests heavily on the upper leaves, a shieldbug moves with deliberate caution across the surface of a plant. Its body forms a compact pentagon, edges smooth, back arched into a subtle dome that catches the light in muted greens and bronzes. From above, it resembles a polished fragment of the vegetation itself, a living shield pressed flat against chlorophyll and stem. It feeds by inserting its needle-like mouthparts into plant tissue, drawing sap upward through a finely tuned pumping mechanism that allows it to exploit the vascular system of its host without dismantling it entirely. In this quiet act of extraction, it participates in a broader web of herbivory, one that shapes plant defenses and seasonal energy flow. Yet the meadow is not a passive backdrop. Predatory wasps patrol the airspace. Birds descend in short, calculated drops. Even spiders wait beneath leaves, interpreting vibration as opportunity. When a foraging bird lands nearby and tilts its head to inspect the foliage, the shieldbug's survival depends not on escape speed, but on sequence. The first phase is subtle. Legs draw inward, lowering the body profile against the leaf. The insect's coloration, already disruptive, aligns with veins and shadows. If the predator's beak probes closer, contact becomes inevitable. At the moment of grasp, the shieldbug activates specialized glands housed within its thorax. These glands synthesize volatile compounds, including aldehydes and other pungent chemicals, stored under pressure until release. When threatened, the bug ejects this mixture through small openings, projecting a fine spray that rapidly disperses in the surrounding air. The scent is sharp, penetrating, and intensely unpleasant to vertebrate and arthropod predators alike. Chemoreceptors within a bird's nasal passages or a lizard's vomeronasal organ detect these molecules almost instantly, triggering avoidance pathways deeply embedded in their nervous systems. The reaction is reflexive. The beak opens, the grip loosens, the prey is dropped. The chemistry here is not random irritation, but targeted deterrence. These compounds can interfere with mucous membranes and taste receptors, creating an immediate negative reinforcement associated with the shieldbug's distinctive shape and odor. Over repeated encounters, predators learn to associate that pentagonal outline with discomfort. In ecological terms, this is aposematism supported by chemistry rather than bright warning coloration alone. The shieldbug's odor becomes a signature that reduces future attacks. Once released, however, the insect does not scramble away in frantic motion. Instead, it collapses into stillness. Legs tuck closer, antennae press against the body, and the shieldbug becomes inert against the leaf surface. This immobility completes the defense. The predator, already recoiling from the chemical assault, now encounters an object that neither moves nor offers resistance. Disgust and uncertainty converge. Continued pursuit would require overcoming both the unpleasant sensory input and the lack of responsive prey cues. In the economy of predation, where energy must be conserved for successful hunts, the calculation shifts. The predator withdraws, attention redirected toward less troublesome targets. The physiology that enables this strategy reflects careful evolutionary refinement. Producing defensive chemicals requires metabolic investment, drawing on dietary resources derived from plant sap. The shieldbug must balance feeding efficiency with chemical storage, allocating energy between growth, reproduction, and defense. Its tracheal system ensures rapid oxygen delivery during the brief muscular contractions that expel the spray, while its compact body design minimizes exposure once stillness is adopted. Even thermoregulation influences the potency of the defense, as warmer temperatures can increase volatility of the compounds, enhancing their dispersal during peak predator activity. In this layered interaction, fake death is not a singular behavior, but a choreography. First, chemical shock disrupts the predator's expectation of a simple meal. Then, absolute stillness removes the final incentive to continue the attack. The Shieldbug does not rely on one mechanism in isolation. It orchestrates physiology and behavior into a unified response that targets the predator's sensory processing. The brain of the hunter, confronted with foul odor and lifeless prey, concludes that the pursuit is no longer worthwhile. Across the meadow, the cycle continues. Plants endure feeding but survive. Predators refine their preferences. The Shieldbug remains, a small architect of chemical negotiation. In its strategy lies a broader truth of survival. Deception is rarely a single gesture. It is a sequence that interrupts perception, exploits reflex, and convinces the pursuer that the hunt has already failed.